Hello, everyone, and thanks for your time in attending this talk. I hope everyone is staying safe and healthy as we navigate through this unprecedented time we're all facing today. My name is Shah, and today I'm going to be sharing some cool and innovative work I did while at UC Berkeley, working alongside Grant Ho, my advisor David Wagner, and a wonderful host of colleagues and collaborators from Barracuda Networks and Columbia University. Our work that we will be presenting today focuses on understanding attacker activity in compromised enterprise accounts at scale. So enterprise accounts are valuable and targeted. An attacker who is able to compromise a legitimate employee account now has access to the enterprise's wealth of business information and functionality, not to mention that employee account's sensitive enterprise emails. In addition, an attacker would be able to potentially launch additional attacks against other users within the enterprise using this trusted identity. And we've seen the damaging effects of enterprise accounts and the compromises and attacks on them in many real-world situations. For example, according to the FBI, business email compromise or compromise of enterprise email accounts resulted in losses of almost $2.1 billion for companies between January 2014 to October 2019. And in most of these situations, attackers developed phishing kits that mimic cloud-based email services, which resulted in the compromise of enterprise email accounts. In January 2015, Zoom Corporation, which was an international wire transfer money provider, reported losses of $31 million due to compromises of email accounts within their finance department. And in 2019, the Puerto Rican government reported losses of $2.6 million due to compromises of email accounts within their government-owned corporation, the Industrial Development Corporation. So these are only a few of the many real-world examples that have taken place in relation to attacks on enterprise accounts. And we can already see that the damages and information that these accounts harbor is quite evident. So to close this knowledge gap and explore building better defenses against attackers in enterprise accounts, we conduct the first large-scale characterization of attacker activity within nearly 160 compromised enterprise accounts across over 100 organizations. We first develop a novel forensics technique for identifying attacker actions on a fine-grained level. And then we use this technique to kind of understand and characterize attacker activity within these accounts. Now, we do note that previous work has studied attacker activity within compromised accounts, but mainly from the lens of personal email and honey accounts. Our work studies enterprise accounts and compromised accounts in the wild. So let's talk a little bit about the data set we used throughout our study. This was a wonderful collaboration with Barracuda Networks, and in total, we were able to study attacker activity across 111 organizations, all of which were active Barracuda customers. We were also able to obtain a set of 159 compromised enterprise accounts across these organizations. And these compromised enterprise accounts were flagged by Barracuda's detectors, as well as confirmed to be compromised by the IT teams at these organizations. Because each organization also uses Office 365 as their email account provider, we are able to retrieve Office 365 application login events for each account. And basically at a high level, what an application login event is it's an event generated anytime a user logs into their account or performs some operation within their account. Now, when an attacker compromises one of these enterprise accounts, there's going to be a mix of application logins from the true user as well as the attacker. So to kind of answer some of the key questions we set out at the beginning, we needed a way to identify which account actions were attacker related and which account actions were by the true user. So our approach uses many well-known ideas in the field of anomaly detection. And it essentially comprises of a set of features and rules based on those feature values. So let's take a simple example. Let's say we have a user of an enterprise account named Bob. We don't know when Bob was compromised, but we do know when Bob was confirmed to be compromised by the IT team at his organization. So let's call this the first sign of compromise for Bob. At a high level, we construct a historical profile for Bob's common login characteristics and patterns using application login events from 1 to 2 months prior to this first sign of compromise. And this historical profile captures Bob's common locations as well as common devices that Bob used when he logged in to his account. Using this historical profile, we can now classify future application login events. So we classify future login events in a 2-month window surrounded around this first sign of compromise. And for each login event we wish to classify, we extract 2 sets of features. One feature captures the suspiciousness of the location within the login event. So how suspicious is this location compared to the set of common locations in Bob's historical profile? Another feature we extract is something called the device user agent, which is basically an identifier string for the device that was used to log into the account. So how suspicious is this device compared to Bob's typical devices that he uses to log into his account? And once we extract these 2 sets of features for each login event we wish to classify, we apply a set of rules to these features. And at the end, we obtain a set of login events that are attributable to the attacker. Now, we do acknowledge that our rule set is not guaranteed to find every attack, nor does it really guarantee robustness against a motivated adversary trying to evade detection. But through a thorough evaluation procedure, which is detailed in our paper, we find that our rule set is relatively comprehensive and obtains a false positive rate of 11% and precision of 94%. So now that we have an ability to identify account actions on a fine-grained level as attacker-related or benign, we can now set out to answer some of the key questions we had at the start. And for the talk, I'm only going to focus on 2 of them for time constraints, but the remaining are detailed in our paper. So the first question we set out to answer was, how long are attackers active in enterprise accounts? So for each account, we find the difference in time between the first attacker event and the last attacker event. And we find some pretty interesting results. What we find is that attackers appear to use and maintain access for long periods of time. In over 50% of accounts, attackers were active for at least 1 day, while in over 1/3 of the accounts, attackers were active for at least 1 week. So an implication of this finding is that non-real-time detection, or detection after the initial compromise over a longer time horizon, can still provide value and prevent significant damage against a lot of these attacks. And to further support kind of this implication, another finding we discovered was that using a third-party data breach alert provider, we found that 20% of enterprise accounts were actually involved in at least one online password data breach. So not only is password use a potential problem between personal and email accounts, but unlike phishing, accounts that are compromised via data breaches won't be detected unless there's continuous monitoring after the initial compromise. So another question that we set out to answer was, what are the types of usage patterns that attackers exhibit in these compromised enterprise accounts? So firstly, in 50% of the enterprise accounts, these accounts had small durations of attacker activity and small time gaps between successive attacker events. And both of these were less than 1 day. So we believe that in these accounts, they reflect a single attacker, namely the same attacker compromises and uses the account for short periods of time. Now, what about the accounts on the opposite side of the spectrum? Namely, accounts with longer durations of attacker activity and longer time gaps between the attacker activity. So we did a more in-depth analysis into these accounts, and we used something called the Jacquard similarity coefficient. So briefly, the Jacquard similarity coefficient is a way to quantitatively measure the similarity between 2 sets of data. So we use the Jacquard similarity coefficient to quantify the attacker behavior that we see before and after these large time gaps. And what we find is that in 31% of all accounts, these suggest that there's multiple attackers at play. So we saw that there was a significant difference in attacker behavior pre and post the largest time gap. And another hypothesis that we suppose is that because we're seeing multiple attackers, the large time gaps between the attacker activity could actually be a sign of credential selling, where one attacker compromises the account, and this large time gap between attacker activity is kind of the transaction window where the first attacker is transferring credentials or selling the credentials to another attacker. So kind of this presence of multiple attackers and this presence that we're finding kind of suggests that attackers are starting to specialize their skill sets in specific roles. Namely, one set of attackers are starting to specialize and develop a skill set in compromising accounts, while another set of attackers are developing a skill set in actually extracting value and using the account. Some other implications that we found in relation to these different attacker usage patterns was that in the 50 accounts that showed signs of multiple attackers, in 30 of them, the second set of attackers actually accessed Office 365 applications at a higher rate than the first set. Now, what this suggests, and it kind of goes along with our previous finding was that non-real-time detection, or if you have a detector that continuously monitors attacker activity after the initial compromise, it can still mitigate significant damage. And in this case, it can try to mitigate significant damage before the account changes hands to the second set of attackers. So overall, our paper goes into a lot more detail, and this talk is only a small segment of them. So if you're interested, I encourage you to read through the paper, which has more results and details, such as a deeper evaluation of our rule set and some other findings that we discussed. And I'm happy to take any questions that you have right now. And I appreciate you taking the time to listen to my talk, and have a great day.